नमस्कार दोस्तों, गुड इवनिंग टू यू। आज हम बात करेंगे लेंसेज लॉ के बारे में और जानेंगे कि लेंसेज लॉ क्या होता है। सो वी विल टॉक अबाउट लेंसेज लॉ टुडे एंड अंडरस्टैंड conceptually how lenses law works. And what I'll do is put it on my, and you can see it and understand it. It's going to be a brief video, but you will enjoy it as usual. And since board examinations are coming very near, थोड़ा सा सीरियस हो जाइए और आप एनसीईआरटी का हर क्वेश्चन कर लीजिए, क्योंकि पूरा का पूरा पेपर बोर्ड का एनसीईआरटी से आएगा और कुछ क्वेश्चन आपके करीब 10% या 5% एनसीईआरटी एग्जाम्पलर से आएंगे। तो आपको पूरी एनसीईआरटी आनी चाहिए इसको अच्छे मार्क्स लाने के लिए। अगर आप तो आप ज़्यादा टाइम ना वेस्ट करें, प्लीज़ डोंट वेस्ट टाइम। lot of questions, in fact most of the questions are from NCERT, so you must be very thorough with every question of NCERT, and very few questions will be from NCERT exemplar, but majorly the paper is going to be from NCERT. So today my request is, और मेरी गुजारिश है आपसे कि आप NCERT पूरी करें और हंसते खेलते आप बोर्ड के पेपर में बहुत अच्छे मार्क्स ला सकते हैं। सिलेबस कम हो गया, लेकिन जो अगर आप सैम्पल पेपर देखेंगे तो उसमें कोई ऐसी बात नहीं है कि सिलेबस काटा गया है, या ऐसा इम्प्रेशन है कि ऑलमोस्ट पूरी किताब पढ़नी पड़ती है। शायद कुछ कम पढ़ना पड़ जाता है, क्योंकि ये साइंस का पेपर है, सब चीज़ें आपस में जुड़ी होती हैं। तो फोकस ज़्यादा रखिए उन चीज़ों पे जो आ रही हैं, जो नहीं आ रही हैं उनको थोड़ा कम पढ़िए, बट पढ़ना तो आपको पड़ेगा क्योंकि वो आपस में लिंक्ड होती हैं। And the students who are preparing for entrance examination, my suggestion is you continue to do everything. Please don't spare any question from NCERT and exemplar. तो जो entrance की तैयारी कर रहे हैं वो NCERT और NCERT exemplar पूरी करें, और एक भी उसमें रत्ती भर की भी गुंजाइश नहीं है छोड़ने की। तो मैं अपना वीडियो शुरू करने वाला हूँ, उसमें मैं आपको ब्रीफली बताऊंगा लेंसेज लॉ के बारे में, और आप उसको कॉन्सेप्चुअली सोचिए कि लेंसेज लॉ क्या होता है और कैसे काम करता है। सो माय वीडियो विल कमेंस शॉर्टली। I just wanted to have a very brief conversation with all the students on how to approach upcoming class 12 board examination. Keep your focus on NCERT, work very hard now, and you should be very successful. So my best wishes are with you, and my video on Lenz's Law starts now. Thank you. Right, so welcome to this discussion on Lenz's Law. Okay, Lenz's Law. So I'll give you a very important concept today. Understand it. This will be one of the questions in JEE mains and NEET examination, or maybe board examination. You do have a question on Lenz's Law in board examination. So look at this loop and then look at this bar magnet. Okay, both are at rest, so velocity is 0 and 0 velocity, and this bar magnet has north pole, and then you have magnetic lines of forces which are coming from and entering the loop. Now what you do is you make a subtle change, and you have this bar magnet being moved now with velocity v. So here it is at rest, and your loop is still at rest, okay? But because you moved the bar magnet, there is a relative motion between these two entities. Now, because of the motion, the number of field lines, is, for example, 1, 2, 3, 4, increases, okay? Maybe it increases by 2. So you have 1, 2, 3, 4, 5, 6 field lines which are coming from the North Pole and entering the loop. So what you have done is essentially you've created a delta phi, which is extra flux, okay, in the loop. In the loop. When I say loop, I mean the area of the loop. Now, the moment this extra flux enters the loop, this loop generates a current, right? Now, the question is, first of all, the extra flux divided by the time it took to, produce this extra flux by the motion of the bar magnet. As per Lenz's, this particular entity, EMF, the voltage which is generated is proportional to delta phi by delta t. So the rate of change of flux produces EMF. This is statement number one. Now, what happens? So the magnitude of fluxes has been understood, right? So the EMF, which is in volts, okay, is proportional to the rate of change of flux. So this is your flux change. It can increase or decrease. This is time in seconds. So this is one aspect. Now, the question is what happens to the direction? So this direction of the current which is induced. So this EMF has got induced in this loop. So the EMF we are studying, this EMF is in the loop and that induces a current. Now we have two choices, right? So the current can be in anti-clockwise direction. And remember, our eyes are located here, okay? So the eyes are located here. Eyes are always located generally, in most of the numericals from, where the magnet is moving, okay, towards an area. Okay, so, but it depends. But generally, when we see the situations, you have to decide where the eye is. So I'm doing this numerical or problem or concept from, eye, which is located here. Okay, so this is the location of the observer. Let's say the observer is here. Now you have two choices. The current which gets induced because of this EMF, either can be anti-clockwise, or, what you can have is this loop, or the current can be, maybe clockwise. Okay, you have two choices. So this is your clockwise, and this is your anti-clockwise. How do you decide this? So the method to do this is the current moves in such a manner so that it opposes this change in flux. If the flux delta phi, which is change in flux, if you change the flux in a manner that it increases, then the flux which is induced by the induced current. So I'm talking about this current, and I can call it I induced, okay? So, current has a magnetic field associated with it. So if the delta phi is the extra flux because of the motion of the bar magnet, so you can see you have 6 flux lines. Earlier you have 4. And this extra has come because of motion of the, so this extra is because of this. And now it has resulted in delta phi by delta t has resulted in EMF. This is induced. The induced EMF has got resulted in I, current induced. And this current now results in induced magnetic field. And this induced magnetic field produces a flux which is induced. Okay? So this current here, I induced, has a flux associated with it. So there are, two terms. One is the extra flux. Okay, so that's your extra flux. The second is your induced. The induced flux is in such a manner that it opposes the change in extra flux. So if I see this, And I say in this particular situation which we are discussing, if I make the current anti-clockwise, which is this, let's say the current is anti-clockwise here. This is my anti-clockwise. And you can see my I is here. So if I look into this, the anti-clockwise direction, my anti-clockwise generation, if I use another rule to be used is the right hand rule, okay? Right hand rule is to be used to decide the direction of flux or the magnetic field based on the direction of induced current. So the induced current has been assumed to be anti-clockwise, and then this induced current will now produce its own induced magnetic flux. And we can see, if the direction is anti-clockwise, then this anti-clockwise, and if you apply the right hand rule to this induced current, I induced, again, you will find that if you hold it, that current is moving in this direction. Your direction of the magnetic field, which is a loop because of this induced current, is like this. Okay, so the flux lines are coming out. So which means that this side will become a north pole because the flux comes out of a magnet and terminates at south pole and then goes inside the bar magnet and a complete loop is created. So anti-clockwise current will make the side facing the observer as a north pole. Okay. So, and you're bringing in north pole. So both the north poles, one is the induced north pole, okay, induced, and one is a north pole of the bar magnet. This is what Lenzs said. If you try to increase the flux by bringing in north pole, then the side facing the bar magnet will also become the north pole. If you take away the north pole from the loop, the induced EMF will produce current in a manner that that side will become a south pole and the bar magnet will feel attractive force towards the loop because it will try to oppose the extra loss of flux. And similarly, you can do this experiment for, reverse situation where the south pole is brought closer to the loop and south pole is taken away from the loop, so on and so forth. And you can have two bar magnets also. Okay. If the concept is clear in your mind, it's very easy for you to decide the direction of the induced current. The induced current produces an induced magnetic field. The induced magnetic field has induced magnetic flux. And that magnetic flux, which is induced because of the EMF, wants to settle, so to say, scores with the extra flux or the loss of flux. Loss of flux happens if you take away the magnet away from the loop, right? So this is what, the Lenzs, indeed go through Lenzs law quickly and be very clear on how to use right-hand rule because this will help you. Right-hand rule is really, really useful. If you understand Lenz's law, you understand Faraday's law. There is not much to be done in this chapter. There are only two laws which should be very clear in your mind. And then you have to be able to identify where the flux changes, how much time it took, area changes, the angle changes. And you can use scalar product to find the flux and then do d phi by dt. So flux change is important, over some time period for you to get some EMF, so on and so forth. So I hope you enjoyed the video and please send me your comments and feedback. I upload a lot of videos on YouTube. You can search for my channel, Institute of Conceptual Physics. And there are around 1,500 videos which you can see. Some of the quality is not good because I didn't have good equipment. So go through them. You will find a lot of numericals out there, which are going to be part of your JEE NEET. Highly probable, not exactly the ones which will come. So thank you very much for your time and I really appreciate your attention. Thank you. Have a great weekend.